Man always wants to go explore what's out there to understand what's happening elsewhere in order to better know his place in the universe. Mars alone is already very far away for us. Traveling to Europa, Titan, or Enceladus is unimaginable since they're even farther away.
In a human mission to Mars, that would be the main thing. So we had several answers, but I think there are a lot more difficulties than just surviving and coming back.
Yeah, and just going there, yeah, that's it. Surviving anyway, it's true that survival is going to be, I think for the first people who go to Mars one day, that's how it will be, I think for sure. But survival, that will be the big challenge, yeah. That's it, I hope it's going to, thank you. Hello, can you hear me? I think so, right? Very well.
Okay.
Great.
I think otherwise, well...
Hello everyone, how are you? I'm very happy to be here with you today, and to be here with you too, Christophe.
Yes, especially since we met a few weeks ago when the documentary was released.
Of my documentary on France Televisions, yes, this science secret, there you go.
So, if we go back to the basics, what's the point of going to space? We already have tools that allow us to observe. Why do we send humans into space?
Well, actually, space exploration started a little over 60 years ago, even a bit more after World War II. And actually there was, how can I say, a push among nations, the great powers, Russia, the USSR, so the Soviets, the Americans, and then the French and the Europeans, to send the first probes, the first launch vehicles, and then humans. So the human aspect actually comes into play just in the context itself, the human nature we have of always wanting to explore. So in the past, we know that humans originated in Africa and then spread out to Europe, Asia, and the Americas. So actually, there's this human trait where people always want to go explore what's out there, to understand what's happening elsewhere, in order to better know their place in the universe. And so already human space exploration is related to that. That's the first reason why we sent humans into space. And then, of course, there are also scientific reasons. Today we send astronauts to the ISS, 400 kilometers above our heads, and it's actually a laboratory, a space laboratory that's literally in orbit, where in fact there are scientific experiments that actually allow us to have an impact on research. Also terrestrial biology, on the understanding really of the Earth and the living beings that inhabit the Earth. So there's also this scientific side alongside the deeply human side where we want to explore, we want to go elsewhere just to see, and also to have this kind of human pride, like we went to the moon, we planted a flag, and maybe Mars in a few years. So yeah, it's also very human, it's a very ancient trait.
All right, why is it so difficult to go into space, to send humans into space?
Actually, I would even say that's a good question, because beyond that, when you think about it, just when you zoom out and look at space, compared to other fields, it's actually very intense what's happening. Because in fact, just going into space, today, not every country, not all the countries in the world can do it, you know? It's a country that really masters the entire process, from building a launcher to even sending its own satellites. There actually aren't that many when you think about it. And it's pretty difficult because these are all very intense phenomena, kind of almost a bit brutal, where actually a rocket, for example, I'll give you an example, Ariane 6, it's a launcher where in 47 seconds you reach the speed of sound. We're supersonic in 47 seconds. We go from a speed of, 0 kilometers per hour, to 28,000 kilometers per hour in 2 to 3 minutes. So it's really, we have a huge difference. And beyond that, besides having to adapt to different environments, there's also the fact that first we're on Earth and then we're in space. Sometimes we even visit other planets, Mars, Venus, which means that actually we have to adapt to different environments, especially for robotic missions. There have been missions to Mars, Venus, and others. First, we're in Earth's environment with the launcher, then we reach space, which is completely different. If we explore other planets, we must adapt to new environments. And so that's what makes things a bit difficult, which means that actually, yes, there's not really a fixed environment. That's not necessarily the case in another field, like, for example, the field that's closest to me, which is robotics or aeronautics. Well, airplanes, when they take off, they stay in the atmosphere at 30,000 feet. So that's an environment we more or less have under control. Space is different, and even when we've been to the moon, well, the moon too, compared to Earth, is an environment that's very different. We're on a celestial body where there's no atmosphere, so no wind, no erosion. There's no breathable oxygen. So it's really that aspect where we have to adapt to the environment and also develop technologies that are very complex, like, for example, a rocket engine. When you think of a rocket engine, it's actually a system where just a few centimeters apart, you can have a part of the engine, which is extremely hot, at thousands of degrees Kelvin, and another part right next to it, not very far away, which is extremely cold, with an almost cryogenic temperature. And so that's also that aspect of it. Engineering technique that is very complex because, in fact, we're dealing with, well, we're going to be exposed to very harsh environments. And beyond that, the astronauts who come back from exploration, it could be from the ISS. When they return from the ISS in the SpaceX Crew Dragon, it's traveling at about 28,000 km/h. And sometimes it's even more. For example, a few weeks ago, there was the NASA Artemis 2 mission where, for the first time in over 55 years, humans went to the moon. They orbited around it and came back. And when they came back, well, they re-entered the atmosphere at a speed of about 40,000 kilometers per hour. And so that creates an environment, actually both thermal and mechanical, that is extremely violent. So in fact, the physics are pushed to the limits of what we can know as human beings. That actually makes things difficult.
By the way, we went to, to the moon about 50 years ago. A lot of time has passed between today and the moment when we want to go back to the moon. What made us take such a long break?
So that's an excellent question. Actually, the Lunar program, Apollo from the start, I think it's important to understand how it began. Apollo actually started right after World War II. We have, well, in quotes, two major historical winners. It's the Americans on one side and the Soviets on the other. There's this aspect where, well, actually we have two great powers that are even dividing up the world a bit. That's why the Korean War happened, and then China, etc. All the wars that are also related to what happened afterward that resulted from it. It's this aspect where we have two worlds facing off against each other. We have a Cold War starting between the Soviets and the Americans. And it's also the moment when this Cold War isn't just, well, political and ideological, it's also, well, scientific. And so the Russians, well, the Soviets were the first to send a man into space and also the first to send a satellite into space. And the Americans at that point are thinking, well, the Russians, the Soviets, they managed to do that. What are we going to do to try to surpass them? Because after all, we're the Americans, we're the best. So what do? Well, at that moment in 58, that's when NASA was born. There are different space centers all over the United States that will end up merging and creating this big agency, which is NASA, which was created at that time. NASA was established at the start of the Apollo program. And so, in fact, this space race begins between the Soviets and the Americans. And the Americans put in a huge amount of money to try to catch up with the Soviets. Really, really a lot. We're talking about several tens of euros per year per American in taxes, so it's pretty huge. And the Americans succeed. So July 16, 1969, Neil Armstrong sets foot on the moon. We had Apollo 11, then we had 12, 13 had a problem, but then 14, 15, 16, and up to Apollo 17. So until December 1972, we had Americans who set foot on the moon and actually explored the moon. Ensuite, then that's when the Americans did it. They said to themselves, we did it. We won this space race against the USSR. Well, now what do we do? Because NASA, we're not going to shut it down either. So now what do we do? And that's when the Americans start to focus a bit more on low Earth orbit, exploration in low Earth orbit. And that's when the space shuttles were born, the space shuttles, so all the STS missions. Space shuttles included Challenger, Discovery, and Atlantis. They originated from the American program where the Americans said, we've done it, the moon, that's great. Now we're going to focus on low orbit. We're going to try to advance our scientific and space-related knowledge in low Earth orbit. And after that, there was everything that followed. The launch of space telescopes like Hubble, Hubble 90, and other quite iconic missions. But alongside that, so this renewed interest in space, and at least in low orbit, also created some obstacles. And these obstacles included fatal accidents for astronaut crews. For example, Challenger in the 1980s. Challenger, a problem with an O-ring seal. The Americans, meaning NASA, had an STS launch with the Challenger shuttle, which exploded after just a few seconds. There were other accidents, like Columbia, which had a thermal tile issue during atmospheric re-entry in the 2000s. And so for the Americans, actually, these accidents affected them quite a bit, really. They were deeply affected. And they said to themselves, we're going to avoid at least for crewed flights, taking so many risks. And now there have to be specific certifications, much more thorough than what existed during the Apollo era. And also actually this lunar aspect as well, it's that, so what you have to remember about the moon, well, it's our natural satellite. It's a celestial body that is geologically dead, where there isn't necessarily, well, it's interesting because it's connected to the Earth. It's believed that about 4 billion years ago, the Earth collided with a celestial body about the size of Mars and formed the moon. So there's also this scientific aspect where we want to go back to the moon to try to also continue to better understand our geological origins from an Earth perspective. But this is tough because going to the moon is expensive. So beyond that aspect where the Americans, they had those traumas with Challenger and Columbia, well, there's also the difficulty of going there with less money. They don't want to spend as much money. And so there's the Artemis program, which is an international program, which as a result means that several countries are putting in money. And that allows in turn the Americans and actually also the Europeans, the Japanese and the Canadians to go back to the moon. So there you go. It's a program that's different from Apollo, which requires different resources with a different goal. Because with Artemis, we don't just want to go to the moon to plant a flag. This time we want to stay there. We want to stay to develop a lunar base at the South Pole and also ultimately to prepare for the journey to Mars. So there you go. So actually the difficulty comes from, well, yeah, technical challenges and certification, especially after the traumas that happened. But also in the end, it's financial because we realize that space and even space exploration, well, without money, nothing happens. Also what we observe is that space exploration always has a boom whenever there is political tension. So in the 1960s, we had the Cold War between the USSR and the United States. That generated a scientific boom where we actually went to the moon. So incredible. And today, well, I wouldn't say we have a Cold War, but we have other types of tensions between this time the Chinese, the CNSA, the Chinese Space Agency, who are actually very, very good, and the Americans. And so this tension, which is kind of a renewal, also creates a technological leap where we want to go back to the moon, and this time to stay there. So actually we realize that technology and space exploration are closely linked to geopolitical tensions every time. And so as soon as tensions are heightened, well, space exploration follows because there's this aspect of soft power that's very important.
All right, so we're hearing more and more about lunar bases. Specifically, where do we stand? Is that possible anytime soon?
So for tomorrow, no, but for a few years from now, yes. In a few years, yes, because, well, NASA has really emphasized that aspect where we want to stay there. The Artemis program was recently reshaped a bit a few weeks ago by the NASA administrator, John Reed Isaacman. He has somewhat, well, scaled back, I would say, the American ambitions for this return to the moon. So there was originally a lunar space station called Lunar Gateway, which was partly developed by Thales. There's Turin in Europe, which has been abandoned. And so now actually the Americans only want to go back there to have a base at the lunar South Pole to stay there. So where are we now? The Artemis 2 mission happened a few months ago. There will be Artemis 3, which will finally be a mission. So that's next year. It's definitely a mission in low Earth orbit. And then after that, there will be Artemis 4, where we're going to land. So I think the goal in the short to medium term for the Americans is to get to the moon before the Chinese, to return there before the Chinese, to set foot, and also to send the first woman to the moon as well. And besides that, well, I think in a few years, maybe around 2030, it might make more sense to think that way. In 2030, there will be the first building blocks of a lunar base at the South Pole. Why the South Pole? Because actually we've detected traces of water ice at the lunar South Pole. So the Earth, I think you all know this, it's tilted about 23 degrees relative to the ecliptic plane, so relative to the sun, which is partly responsible for the seasons. So actually the Earth's poles, there's a part of the year when they're facing the sunlight and another part of the year when they're actually a bit farther away. The moon isn't at 23 degrees, it's at about 1 to 1.5 degrees, meaning the moon. At its poles, there aren't necessarily big differences over a year, or a lunar year, or even an Earth year, whatever. There are areas that are constantly in the light and others that are constantly in the shadow relative to the sunlight, which means that in shadowed areas at the bottom of certain craters at the lunar South Pole, there are places where, well, actually, it's been in shadow for billions of years. There has never been any light, never a ray of sunlight that has reached that crater or certain craters. Which means that with meteorite impacts that send minerals and deposit, well, substances that can be interesting, we've found traces of water ice that have remained that are actually, well, persistent in those craters. And that can be interesting both from the point of view of astronaut survival on the moon, so actually everything related to electrolysis and, well, survival management. And we also have issues related to fuel. So these traces of water ice, actually, well, water, H2O, hydrogen, oxygen, when you separate them, it makes rocket fuel. It could eventually allow for a trip to Mars as well and generate a resource that will be important for interplanetary travel. So we have an area that's interesting and actually an area that all the major powers are kind of fighting over. I think the Chinese, whether they reach the moon before or after the Americans, will also want to stay close to the South Pole for its valuable resources.
All right, so there's kind of a competition between different countries to be the first to establish a lasting presence. So does that also create geopolitical problems? Can you actually own a piece of the moon, have lunar territory?
I believe the Outer Space Treaty states that nothing in space officially belongs to any country. Well, you know the Americans, they always have a flag to plant, but I think the Americans, they're going to do it. I think they're going to plant the flag. But officially, you know, space law, the Outer Space Treaty, says that they don't necessarily have the right to say this is ours and only we should use these resources. I think as a result, the Chinese might come too. So actually, I don't really know how it's going to go. It could also create tensions in the 2030s because of that. They might have to come to an agreement too, because both powers will be able to go back there and stay. So inevitably, there will be a point where the political side or even just the legal side of things will definitely come into play. But today, well, officially, no, that's not the case. There isn't really any lunar zone that belongs to any particular country or that will belong to one or anything like that, no.
Okay. And what about Mars? Because sometimes we hear all kinds of different opinions. Some people are extremely optimistic, and for them, a Martian base will be built by 2030. There are others who are much more pessimistic. Where are we at? And why does it seem to be so complicated to put a base on Mars?
Honestly, we're nowhere.
Hiya, Mars?
Well, so Mars, actually, we send robots there, rovers. So there was Perseverance, Curiosity. Those are, well, the robots that are now kind of emblematic of NASA. Those rovers, actually, there's Curiosity, which is in a crater called Gale Crater. There's Perseverance, which is very, very far from Curiosity in a crater called Jezero Crater. These are craters where we think that millions or even billions of years ago, there was water. So we know that Mars potentially looks or looked like Earth, like present-day Earth, even though today the conditions are completely different. Where are we now? Well, we have, in terms of unmanned robotic missions, we are able to go to Mars. We are able to land there. Not all powers, but the major ones can do it. On the other hand, sending people, now that's something else, because actually sending people, the human aspect is so important. And actually, I don't know how to explain it, but just getting to Mars already takes 6 to 9 months. The moon, it's 2 to 3 days, well, about 4. So it depends on the orbit and also what we do before, etc. But Mars, let's say between 6 to 9 months. But one thing that's also important and that we have to take into account is that Mars is a planet. So Mars, obviously, it's not like the moon. The moon orbits around the Earth. The moon is constantly, on average, 384,000 kilometers away from us. With Mars, it varies. So Mars, when it's closest to us, it's about 50 million kilometers away. It takes 6 to 9 months. But then you have to wait 26 months for Mars to come back closest to Earth so we can return. If we leave and return, the trip will take over a year, possibly 2, since we must wait for Mars and Earth to come close again to return. There's also the issue of how long the trip will take. Because today, on the ISS, long-duration missions, well, right now we have Sophie Ann No, who is currently on the ISS. She's on a mission of about 9 to 10 months, I think. About 8 or 9 months. That's about the maximum we can do. There's never been a mission on the ISS where they've really stayed, well, as a deliberately planned mission for 2 years or 2.5 years on the ISS. There really is a rotation of astronauts. Generally, it's every 6 months. So it's extremely far from Earth. Mars is just a tiny dot in the sky, so it's really extremely far away. There's the distance aspect, but also the matter of conditions. The Martian atmosphere is made up of 96% CO2. We, as human beings, well, CO2, you know, we need oxygen to breathe. So it's a bit complicated because of that. And beyond that, even the conditions, well, a Martian summer, when the weather is nice, it's 20 degrees. So that's okay. That's okay. but it can go down to minus 150 degrees. So yeah, there's that side where we think, okay, we can just go as we are, but in the end, no. And then besides that, the problem with Mars is the atmosphere. The Martian atmosphere is much thinner than Earth's atmosphere. So Earth's atmosphere has the ability to protect us. Also, thanks to its magnetic field, the Earth protects us from all the UV radiation and dangerous rays coming from the sun, which is not the case for Mars. So on Mars, if we're not well protected, it can eventually, maybe not instantly, but over time, cause cancer and have an impact on our cells for us as human beings. There's also that factor. The main issue on Mars is the human element, not the environment. We know how to send robots and even travel to Mars. The real challenge is the human aspect. When will we get there? Well, that's a good question. For me, it's a bit complicated to say because honestly, we don't really know how the technologies will evolve and so on. Well, we have SpaceX with the Starship that wants to go there. Personally, I would say maybe 30 or 40 years. Maybe I'm a bit pessimistic, but that's how I see it. For me, well, first of all, I'm one of those people who think that we are meant to live on Earth. The only planet that suits us is Earth. We should take better care of Earth and protect it before going elsewhere. So that's it.
Okay, let's return to the topic of space exploration. Why Mars in particular, when there are other planets that sometimes seem to have advantages that Mars doesn't? Why do we want to go to Mars and not to others?
Well, actually, when we look at the other planets, well, let's talk about the Sun. At 57 million kilometers, we have the first planet, which is the closest one. That's Mercury. Mercury, no atmosphere either. Mercury, a temperature of 420 degrees. Okay, we want to move on. Let's go further. 108 million kilometers, Venus. Venus is rocky like Earth, okay? Then we think that's nice. With a diameter of 12,000 kilometers, a bit like Earth, we think that's very nice. We think, okay. But on the other hand, when we get there, when we look at Venus in more detail on the surface, 465 degrees, an atmospheric pressure of 92 bars, so a pressure 92 times higher than what we have on Earth. Sulfuric acid rains, an atmosphere that moves 5 times faster than its surface, extremely violent winds. All right, Venus aside. Next, there's us, Earth, about 149 million kilometers away. Mars is next and is a bit farther away. And Mars actually, in the end, when you look at it, it's the only rocky planet that has conditions that are somewhat similar to Earth's conditions in terms of temperature. But even Mars is complicated, as I mentioned, because its atmosphere contains chemical elements, and the atmosphere doesn't help us. And then, in that case, we'd have to look elsewhere. But if we go elsewhere, Saturn, asteroid, Jupiter, Saturn, Uranus, Neptune. So Jupiter, we can already forget about it because it's a gas planet. That's it, we can't go there. Hydrogen and helium, nothing we can do. Now, Jupiter and Saturn are 2 planets, so gas giants that have moons, more than 90 moons and 100 for Saturn. Among these moons, there are some that are interesting. For example, Jupiter has a moon called Europa. There is a NASA mission that was launched in 2024 called Europa Clipper, which will arrive at Jupiter in 2030 to explore Europa, which is one of Jupiter's moons. So we have celestial objects, celestial bodies that can be interesting because they have an atmosphere, they have, well, conditions where we can say, okay, there could be life there. But actually, we realize that even Mars is very far away for us. Going to Europa, Titan, or Enceladus is something we can't even imagine because it's even farther away. Jupiter is more than 700 million kilometers away from the Sun. Saturn is more than 1 billion kilometers away. So we're talking about distances that are beyond what I think a human being can do simply by being human. So that's actually the reason why we focus more on Mars and why there have been more Martian robotic missions than Venusian missions. There have been Venusian missions. But as for Venusian missions, just so you know, the space probe, the robot that landed on Venus and stayed the longest, it lasted 127 minutes. And after that, nothing. Because the materials can't withstand it, the conditions are so extreme, it's just impossible. So yeah, it's sad, but it's a bit complicated. In the end, really, we realize, yeah, Earth is truly our friend. We're happy to be here. We're happy to be here today in Paris. And that's it, we're happy, we can drink water, we can breathe well, that's cool.
And about signs of life, because sometimes we hear announcements that traces of life may have been found on certain planets. So where exactly do we stand on that?
In the solar system, where do we stand? We know that around giant planets, gas giants like Jupiter or Saturn, there are moons that could be interesting. Europa, Titan, and Enceladus. Europa, for example, what's our status? We know it has an ice crust several kilometers thick beneath its surface. But actually, beneath that ice crust, there's an ocean of liquid water. And actually, this ocean of liquid water has been observed. It has been detected by NASA instruments and even instruments from around the world where they've detected, in fact, irregularities, but also simply a magnetic field around Europa. And actually, that means we know there's potentially an ocean of liquid water deep down. That's why we're sending the Europa Clipper mission. So we have celestial bodies where we know there could potentially be something, but actually where we stand right now is that we haven't really found anything. In fact, we haven't found anything at all. We're sending probes to learn more and understand better. Maybe one day we'll have an answer. But just knowing that there's no life is already an answer. So right now, the fact that we don't know justifies sending probes. But so actually, in the solar system, well, I'm one of those people who think that life elsewhere is certain, but elsewhere in our galaxy, elsewhere in the universe, yes, but not in our solar system. I think that in the solar system, I think we're the only ones. That's just my opinion, but as things stand, we're sending probes and eventually we'll probably get answers, but not right away, maybe in a few decades. All right?
Do we have a chance one day to be able to go to other solar systems, or with current technologies, or even in the near future? Is that completely out of reach? So
right now, it's completely out of reach. Unfortunately, sorry to crush those dreams. It's a bit sad, but we have a probe at NASA called Voyager. Well, actually, there are two probes, but Voyager 1, which is now more than 24 billion kilometers from Earth, was launched in 1977. And just so you know, right now it's going to reach 1 light day away, even though it was launched in 1977. So it's leaving the solar system. Well, it's officially in interstellar space now, I think. And the thing is, at that speed, it's leaving the solar system at over 61,000 km/h. That's extremely fast, really fast. You see, we're not talking about trucks here in Paris going at 30, right? Or, we're not on the ring road here at 50. We're really talking about a speed of 61,000 km/h, so that's really fast. And the thing is, at that speed, considering where it is right now, just to reach, well, the stars that are in our galactic neighborhood, it would still take us several tens of thousands of years of travel. So at this point, we think, well, we're happy we can get to Mars and so on, but actually Mars, on the scale of just our solar system, is right next to us. It's really close to us. I'm not even talking on a galactic scale. In the end, it's unfortunately out of reach. We put a golden record, kind of gold plate with drawings that show, well, we're here, we're human beings, we're on Earth. If one day aliens come across this probe, in 20,000 years, 30,000 years, but the probability is very low, and actually, it's the distance that's the problem. That's why we're developing space telescopes, actually, like Hubble, James Webb. These are telescopes we're developing because going there is just way too far, actually. And the distances, and I think that even we as human beings, our brains can't even realize just how big the Earth is. And beyond the Earth, the distances are so vast that that's kind of what causes problems and makes it out of reach. There you go, thank you.
but then it could be a little bit depressing. We might think that in the end, space exploration isn't very useful if in fact we're stuck because of these distances.
Actually, we're blocked by these distances, at least for now, but space exploration also helps us understand where we come from as human beings and the history of our planet, Earth. And we know that our planet, Earth, is inevitably connected to the other bodies in the solar system. About 4 to 4.5 billion years ago, the Sun formed amid an accretion disk, with collisions creating a chaotic early solar system. We know that in the end, everything is somewhat connected, more or less. And so studying and exploring elsewhere in our solar system is also, in fact, indirectly, well, a way to better understand our own geological and biological origins on Earth. So there's this aspect where space exploration, I think as long as we stay within the solar system and try to better understand our own planet, well, in that case, it makes sense. But going elsewhere to observe other solar systems, to look for, signs of life, well, unfortunately, there's this issue of distance that gets in the way. So for me, it's still useful. And there's also the exploration aspect, because when we talk about exploration, well, there's crewed human exploration, but there's also all the activity in low Earth orbit, which is important for us, for GPS, for weather, for climate. You should also know that, for example, at the European Space Agency, ESA, much of ESA's budget isn't for human exploration. Well, there is still a part of the budget for that, but the biggest part of ESA's budget is really for activities related to Earth observation. So these are things that are connected to us. So actually, we're using space to serve humanity. So space exploration also has this aspect where it serves us as human beings in our daily lives every day, and it also helps us move forward in our daily routines and makes our lives easier.
All right. At the same time, we can transition to the different questions to see a bit what people have answered. So our first question was about how long it takes to reach Mars with current technology. So
there you go.
Well, yes.
That's exactly it. It's about 7 to 10 months. That's the time it takes to get to Mars. Well, for Jupiter, when we go beyond that, well, we're talking years. But for Mars, that's exactly it. It's about 7 to 10 months. Yeah.
All right. Next question. So on Mars, can we go outside, get some fresh air, so to speak?
I would have liked to, but yeah. Unfortunately, no, that's not the case. Be careful. It's the conditions. It's also the chemical elements present.
The pressure is about how much compared to the
Earth? It's much lower than on Earth, so I think it's about 4 to 5 times lower than on Earth. And actually, the level of oxygen we have in the Martian atmosphere, we have about 97% CO2, and I think it's 0.13% oxygen. Unfortunately, it's not possible. We're even more limited on Mars than on Earth.
All right, okay. Next question. Why is going to Mars much harder than going to the moon? Yeah.
That's exactly it. 90 is impressive.
That's good, huh? It means they really paid attention.
No, that's impressive. That's impressive. And, well, yes, that's exactly it. It's simply the distance. The moon, actually, when it's at its perigee, I think it's 356,000 kilometers. When it's closest to Earth, but at apogee, it's 406,000 kilometers. And so it's always around us. So actually, the moon, in the end, we have control. We've already been there. So going back, we can do it too. And in that sense, it's very close. But Mars, it's true that, as I mentioned, when we're on Earth, sometimes we can see Mars with the naked eye from the northern hemispheres, but it's just a small reddish dot in the sky. It's extremely far away. We're talking about millions of kilometers, so it's a whole different scale.
All right. Next question. The hardest part of a human mission to Mars would mainly be... So we had several answers, but I think there are a lot more difficulties than just surviving and coming back.
There's just getting there, yeah. But surviving, in any case, it's true that survival is going to be I think for the first people who go to Mars one day, that's how it will be, I think, inevitably. But surviving will be the main challenge. For sure, survival. How are we going to keep a crew alive on another planet so far away? That's really, yeah, that's going to be the biggest challenge, yeah.
All right. Next question. The Voyager probes are currently...
In interstellar space, yes, we discussed Voyager 1 and 2.
Are they already there, or have they not crossed it yet? I think they're already there.
They're there, they already are. So officially they already are. At a distance that's great enough to say that officially we're in interstellar space. I think Voyager 1 is heading straight toward an exoplanet that's located 17 light years from Earth. And Voyager 2, I don't remember exactly, but it's heading off in another direction. But today, it's Voyager 1 that's really the man-made object that's the farthest from Earth.
We have one last question left. What is the most accurate statement about Mars, then?
Well, yes, it's a second Earth where we could live outside. Well, unfortunately, no. It's a hostile world, so we'd need to go quickly, exactly. Compared to their surface activities, that's it. And is it an ocean planet? No, not that either. There are ocean planets that we've detected as exoplanets, so elsewhere in the galaxy. But in the solar system, at least for Mars, no, it's not an ocean planet, unfortunately. Even though we think it had water billions of years ago. So that's also why mobile instruments like Perseverance and Curiosity are on Mars, to look for traces of fossilized life. And also to search a bit. Well, since as human beings we know that our life as we know it, at least here on Earth, is connected to water. Well, in the end, going to Mars, knowing that there was water, potentially it's also about whether there was life on Mars before. So that's it. But in any case, yeah, that's the answer, exactly.
Okay, so that was the last question. Thank you very much. Thank you very much for this interview. So now we will also be able to have Daniel Kent join us to answer some of your questions.
There you go.
So don't hesitate. There should be microphones going around on the right and left if you have any questions to ask.
I had a question.
Can you explain to me what an exoplanet is? What? So,
An exoplanet is, in fact, yes, by definition, it's a planet that orbits a star other than our sun. So our sun is a star, it's a yellow dwarf star. There are about 20 yellow dwarfs in the galaxy. 70% of the stars in the galaxy are red dwarfs, and an exoplanet can orbit different types of stars. So it's simply a planet that orbits a star other than our sun. So elsewhere in the galaxy or even in the universe, São Paulo, I don't know if it's close. Why have I never answered?
but there are also rogue planets that aren't even associated with any stars.
That's true, that's true.
We actually found that quite recently, by the way, planets that must have been ejected from their birth star.
Is that also considered an exoplanet?
Yes, those are planets, wandering planets. Well, planet already means wanderer, but yes.
That's true, that's true. It's a technology, yeah, that's true. I have a question here. Yes, multiverse,
Science fiction fantasy possibility.
Well, I'm kind of on the science fiction team though. For me, it's kind of science fiction. I'm on the science fiction team when it comes to the multiverse. But actually, I think, does physics really reject the idea of the multiverse? No.
Not at all. The equations as we write them, you write the equations formally, and you have two parts in an equation. You put a certain number of precepts on one side, and on the other side, you put everything needed for those precepts to be fulfilled. And then we look at nature to know what needs to be put in. Because the equations, they are formal. They can tell you anything and everything. And in particular, nothing forbids that the global equations of the universe, nothing rules out the possibility that there could be several possible universes. There are multiple solutions. There can even be much more than what we can handle. And the idea of the universe and the idea of the multiverse came as an additional hypothesis to try to explain the contradictions we faced when we wanted to understand why the universe seems so finely tuned to our own existence on Earth. That's it. So people thought, well, after all, maybe we're not the only universe that exists. Maybe there are others. And this is absolutely not in contradiction with the laws of cosmology. Now, does that mean it's scientific? It's scientific to the extent that it's predicted, but that doesn't mean it actually exists. I can very well imagine that there are green elephants with pink spots somewhere on another planet. Even if biologists tell me that it's not impossible, that it's plausible, as long as I haven't observed it, nothing proves that it exists. You see, so just because it's scientific and rational doesn't mean it actually exists. If we haven't observed, we don't know. A question in the back? Yes, the observation.
For example, today we were talking about standard models. Maybe one of them is the Shane planet model. You see, on the other hand, today there are models that also challenge the standard model, allowing us to actually explain a little bit later on what it is. Dark, the matter that actually allows us to explain, in this situation, a little bit of the various evolutions, dark energy, dark matter. Is there actually today an opposing theory that no?
I don't think so. I think that today, as our late colleague Hubert Reeves used to say, it's the best model we have on the market. That's it, to put it that way. It's a model, it is what it is. It bothers some people, it satisfies others. There aren't that many assumptions behind it. Afterwards, it's still quite complicated because to get to it, it's a bit like the Ptolemy system. We realized that some things don't work. So we add certain elements, we refine it, and so on. And as long as it doesn't become untenable, as long as it's not completely artificial, well, we keep this system, we stick with it, and there are indeed tensions. I called it tension earlier. There are others, that concern us. For example, the fact that the universe, when you look this way and that way, shows the same properties. Even though these are regions of space that have never met, that are not connected by any causality. So we found, that string theory, for example. Pardon? So we found the inflation system to explain that. Then you need, that's something else from string theory. It's to understand what's happening at the level of the singularity. And there you actually have other options as well. But these options do not call into question the launch of the Big Bang. It's simply a way to understand how to get around the singularity. So there are still a lot of tensions, but overall it's still quite extraordinary that we get so many satisfactory results and often even predictions. There are things we've managed to predict. For example, with the model, we can predict gravitational lensing. We managed to predict the arrival of an image a few months after discovering one. Another one came to us and we observed it on the plate because it had followed a different path from the previous one. And so these images arrived at different times because they didn't travel exactly the same path from the source to us. So there are still some things that are extraordinarily predictive. And then there's also the fact that there are several ways to get matching results through completely different approaches. For example, what we call nucleosynthesis of elements, meaning understanding what happened during the first 3 minutes just after the Big Bang. Well, that's something that gives results that are completely in line with what we observe around us, the abundance of elements. The nucleosynthesis inside stars, through nucleosynthesis, that is really the structure of atoms, we get extremely interesting results in the context of the Big Bang. And we also get results if we study the dynamics, etc. So these are different ways of thinking about the universe, of studying it. And for now, we are able to achieve remarkable agreement. So there you go. I wouldn't say, I'm not a Big Bang Ayatollah. Actually, Ayatollahs in general don't really like that. But I would say it's still the best model we have. Well, let's continue with it as long as it gives us interesting results.
And that won't be what we'll talk about beyond the white wall in any case. And that won't be what we'll talk about one day beyond the Planck wall.
No, we can't go past the Planck time. All right.
In any case, don't hesitate to follow us on YouTube. We'll be able to put up the replay and plenty of other replays on the YouTube channel. And we'll be able to do more conferences on other topics as well. So don't hesitate to stay updated. Thank you very much in any case.